Have you ever wondered how water can exist as a solid which cracks in straight lines? Or exist as liquid which can break into a million pieces and reform undamaged? How can it turn into a gas carrying so much energy? Why do gases become light when they are warm? How can we predict the behavior of gases so we can use them to do our bidding? The explanation is simple, yet one of the greatest scientific discoveries of all time. Matter is made up of particles. If we shake a group of spheres, they will stack neatly. If we look closely at crystals, the first thing that strikes us is that the angles are so precise and the faces are so flat. How can they be so regular? The answer scientists give is that when crystals grow, they build up layers of particles. Salt crystals are formed by precipitation and crystallization. As the water evaporates away, the charged ions bond together where there is room and the charge is right. They drop out of solution and settle. We would like to zoom in closer and closer to show the particles. Unfortunately, the particles are smaller than light and we cannot see them, so we have to find them by deduction. The particles can be single atoms or combinations of atoms called molecules. In a salt crystal, the particles are charged atoms or ions. If these ions are all the same size, the crystals will form like a cube. This is common salt. The crystal shape is known as cubic. Here, atoms of lead are gradually depositing onto the crystal. This time they form as we pass electricity through the solution of lead nitrate. It builds up to form a beautiful lead tree. The shape is a fractal, but that is another story. If a particle has mass and is moving, then it has kinetic energy. This is gas close up. The kinetic energy of the particles determines the temperature. The more we heat the gas, the faster the particles move. The gas will either expand or increase the pressure on the walls, all due to the increased movement. If particles hit our skin, we feel the impact. We feel it as warm. If they travel faster, then they will hit harder. We detect this and call it hot. When they have enough energy, they will do damage. We feel painful burning. When a comet passes through the solar system, it leaves behind it a trail of rocks. At certain times each year, the Earth passes through these old trails. Our atmosphere hits them at great speed. So why do the rocks get hot and disappear before they hit the surface? At absolute zero, the particles in a solid are perfectly still. If we heat them, we are actually causing them to move apart, so this movement causes the particles to take a little more room, and the material will expand. More movement, more vibration, more thermal expansion. And of course, if we cool a substance, the molecules will slow down and the substance will shrink. When Napoleon was fighting in Russia, he sometimes supplied his troops by sea. The Russian winter was far colder than his navy was used to. On a man-of-war sailing ship, the cannonballs were held in place by a brass cage called a monkey. It sometimes became so cold that the cannonballs shrank. The brass bands tried to shrink even more, but they couldn't, so they snapped. And this is the origin of the ancient expression, cold enough to freeze the balls off a brass monkey. This model shows what happens as molecules are vibrated. At first, the solid is broken down to liquid. Then, as the particles receive more kinetic energy, they break away from the liquid and become gas. When a substance dissolves, the particles leave the solid gradually and move with the liquid. Because Condi's crystals are so beautifully colored, we can see where the particles are. When they dissolve in water, small particles spread out evenly into the liquid. Even if we dilute it 1,000,000 times, the color is still even. So, in the original crystals, there must be at least millions of very small particles. The particles must be smaller than the pores in this very fine filter paper. The same with this fine suspension of sulfur. We call this a colloidal suspension. Milk, which is small drops of fat suspended in water, also passes through filter paper. We call this an emulsion. Light wafers are extremely small. They pass straight through the solution. The colloidal particles of sulfur are large enough to scatter the light. And the emulsion almost blocks it. What do these experiments say about particle sizes? Particles in a typical gas move extremely fast, about 1,000 meters per second. How do they interact with large suspended particles? This is smoke close up, large particles of solid being bombarded by molecules of air. The smoke can be from anything smoldering. You need to try this yourself to see it clearly. The movement of the smoke particles is called Brownian motion. If we watch a colored salt dissolving, we will see the color gradually spread or diffuse. This is because the water molecules are hitting the dissolved salt particles, moving them around.
Sit down. Sit down. Oh, good boy.
The fast movement of gas particles is also the reason why a smelly dog can be smelt as soon as it enters the room. The smelly particles travel as a gas very quickly.
Oh, poo. Poo.
These two diffusion tubes contain the colored gas bromine. One contains bromine only, the other contains air as well. The bromine liquefies as it reaches the bottom of the tube where it is cooled. In the bromine-only tube, it liquefies rapidly. But in the tube containing air as well, this process is much slower, as it takes longer for the bromine to reach the bottom. The reverse is seen as the tubes are warmed. As the bromine evaporates, it diffuses upwards. With no air, this is rapid, but why with air present is the diffusion so slow? A mixture of gases, each with different sized molecules, can be separated by a membrane with small holes. It acts as a sieve, letting the small ones through. The large ones would bounce away. Electricity, too, is made of particles called electrons. When they pass through water, one electron releases an atom of hydrogen and two electrons release an atom of oxygen. This process is called electrolysis and is used to produce hydrogen and oxygen, after which heavy water remains. Hydrogen has three different forms called isotopes. Each has a different mass. They are all attracted to the electrode, but the lightest one gets there first, leaving the heavy ones behind. Have you ever wondered how sound gets from the speaker to your ear? As the speaker diaphragm moves back and forth, it pushes particles of air with it. This movement causes pressure fluctuations that can be detected by the ear. This animation is oversimplified. If we place frozen carbon dioxide into water, the carbon dioxide boils off. It carries with it a fog of water drops, making it easy to see. This simple experiment shows that gas has mass, and this gas has more mass than the surrounding air. The carbon dioxide molecules are heavier than air and sink. This flask has air in it. We can weigh the flask, but we cannot weigh the air because it is buoyant and is floating in the surrounding air. We can use a vacuum pump to remove the air. The flask is now lighter by the mass of air removed. Let's look at a larger volume. This frame encloses 1 cubic meter of air. This much air weighs 1.3 kilograms, more than this liter of milk. The atmosphere is held in place because it has mass and is attracted by the Earth's gravity. Molecules shooting out into space are slowed down and brought back by Earth's gravity. Hydrogen and helium escape because they travel so fast. Planets with small gravity have lost their atmosphere as the molecules shoot off into space. Atoms and molecules are surrounded by negatively charged electrons. In a collision, they repel each other without any loss of energy. Their collisions are perfectly elastic. They make no noise and lose no energy. If we left a gas perfectly sealed, it would continue bouncing forever without ever slowing down. Molecules have mass and velocity, so they have momentum and kinetic energy. As they bounce back off the wall, the momentum changes due to change of direction. This applies pressure to the walls. There is no change in kinetic energy because the collision is perfectly elastic. If molecules of different size collide, we would expect this to happen. No kinetic energy is lost. Moving particles exert a pressure on the walls by their collisions. pressure acts in all directions. Here, water pressure is forcing the water jets in all directions. With this pump, it looks as if the water is being sucked up, but suction is not what it seems. The plunger is making room, and the air pressure is pushing down on the surface and forcing the water up into the tube. When molecules combine in a chemical reaction, the making of bonds can release energy. The molecules then increase their speeds dramatically and increase the pressure. This is how explosives work. The chemicals combine, a huge rush of gas is produced, and this pushes outwards. If it happens fast over a short time, it is a high explosion. This will fracture rock because the rock does not have time to move out of the way. Petroleum burning with air is a low explosive. The products of the burning have high kinetic energy and push the piston down. Gunpowder is also a low explosive. It has plenty of energy, but it gives off the gas gradually. It continues to push the steel ball as it accelerates up the barrel. A high explosive would crack the barrel. The gas is pushing just as hard on the cannon as it is on the cannon ball. As a result, the cannon is pushed back. This is called a reaction force. In a jet engine, the explosion is continuous. A jet engine is a fire in a chamber with one side missing. Fuel and air are forced into the chamber where they combine and expand due to the heat of combustion. The gases push on all sides except the side that isn't there. The collisions on the side walls apply force, but cancel out because the forces are in opposite directions. The collisions on the front wall, however, are not balanced out because there is no back wall. An aeroplane propeller works in a similar way, though it is not at first obvious. The propeller pushes and accelerates air particles backwards. The air being accelerated exerts an equal and opposite force on the blades pushing the plane forwards. It only works because the air particles have mass and velocity. A helicopter is the same thing, except that it is sending the air downwards. The particles making up gas have kinetic energy. We measure this as temperature. The faster the particles, the higher the temperature. If it hits something, it will set the particles of the solid vibrating. We say it has warmed it up. Even more vibration and the solid will melt. It can even hit so hard it will knock particles out of the liquid. We say the liquid has vaporized or evaporated to form a gas. If it hits another molecule with enough energy, it can break it apart. We call this decomposition. We all know that water boils at 100 degrees Celsius. The steam produced is 100 degrees also. This is known as saturated steam. It will condense as soon as any heat is removed from it. However, if we heat the pipe, the steam will become superheated. It is possible to have steam red hot and glowing in the dark. The superheated steam is then able to burn paper. The paper is being decomposed by fast-traveling particles of steam. If we heat it more, it can be made hot enough to light a match. It is obvious to anyone who has blown up a balloon that the air has volume. The more we blow, the more volume. Because a gas is made of fast-moving particles, a gas will always expand to fill the space allotted to it. No matter the shape, the gas will fill the space evenly. If we boil water, we can collect the steam, and it is obvious that it occupies a space. It has far more volume than the water it was made from. The same happens with carbon dioxide. The volume of the gas is over 1,000 times the volume of the solid. So, a sample of gas has volume, temperature, and pressure because its particles have mass, movement, and kinetic energy. They transfer this kinetic energy in collisions. To study these variables further, we examine them in pairs. This is an airbag saving a dummy from facial damage in a car crash. We use the fact that gas has volume and can apply pressure. But how are pressure and volume related? What happens when we double the pressure, or 3 times, or 4 times? This is what the graph looks like if we graph volume against pressure. However, we need to allow for atmospheric air pressure, which is the same as adding a brick to all the readings. So we move the axis to the left by 1. The curve is a hyperbola, but it is very difficult to be sure of this and to find the relationship between the variables. So we plot 1 over volume instead, and the line comes out straight. Pressure is proportional to 1 over volume, or inversely proportional to volume. As you go higher in the atmosphere, there is less air, and there is very little air pressure compressing it. A helicopter at ground level may be able to lift 5 tons, but here in the mountains of New Guinea, it is struggling to lift 1 ton. Because of this, every helicopter has its ceiling where it can no longer carry any load. High in the Himalayas, mountaineers and trekkers have trouble breathing because there is less air. The Sherpas have far more blood cells to carry oxygen.
You have a lot less energy.
If we take a balloon and cool it with liquid nitrogen, the air will contract. The colder a gas becomes, the less volume it occupies. The particles have slowed down and don't push as hard on the balloon. The atmosphere pushes it in. After a few moments in the warm air, and it picks up movement through the rubber, the particles pick up speed and the gas expands again. This is called a gas thermometer. It is simply a flask with gas, in this case air, connected to a tube full of colored water. In ice, the gas particles slow down so the gas has less volume. Now, if we heat the gas, the particles pick up speed and the gas take up more volume. In 1802, both Gay-Lussac and John Dalton heated gas from 0 to 100 degrees Celsius and found the volume increased to 1.375. The particles occupy a volume because their velocity is enough to push the outside atmosphere back. Now, if their velocity is increased, they can occupy a larger volume. So, as the temperature increases, so does the volume. When the air in a hot air balloon is heated, the fast particles push out some of the air and the remaining air is lighter, so it floats in the surrounding air. In 1805, Laplace, looking at Gay-Lussac's results, proposed that a relationship should exist between temperature and pressure of a fixed volume of gas. This is a sphere containing air at 0 degrees Celsius. The pressure is 1 atmosphere. We plot it on the graph. Next, we heat the air to 100 degrees Celsius. The pressure has increased. If the gas is cooled to minus 73 degrees, the pressure decreases. The graph is a straight line, so pressure and temperature are proportional to each other. But what if we extend the graph to 0 pressure? This also works in other ways. Firstly, if we squeeze air, it gets hot. This is how some Malayan tribes made fire using a plunger in a bamboo tube. The air becomes hot enough to ignite tinder, in this case, cotton wool. We use the same principle in a diesel engine. With a high enough compression, the air-fuel mix becomes hot enough to ignite. A diesel engine does not need a spark plug. Without electrics, the diesel engine is very reliable. If instead of compressing a gas we let it expand, its temperature drops. As we release compressed carbon dioxide from a fire extinguisher, it becomes very cold. In fact, some of the carbon dioxide freezes. This is how dry ice is made. A refrigerator is a heat pump using both compression and expansion. The gas is first compressed and gets hot. However, the hot compressed gas is cooled to room temperature in the coils at the back of the fridge. Now it is allowed to expand and it cools below room temperature. Magic, but difficult to understand. By understanding how gases behave, we can tame them to do our bidding. All around us, gas laws are operating unseen, misunderstood, and often unloved.